Okay, this is lecture 18, Physics 112. Now I'm going to talk about dielectrics and dielectric filled capacitors. So before we talk about, previously we have talked about these parallel plate capacitors, and between the two plates there is nothing or just dry air, right? So let's just say air because it's hard to make vacuum. And the capacitance is given by C is equal to epsilon naught A by D, where epsilon naught is what we call the permittivity of free space. That's permittivity. And now the numerical value for that thing is epsilon naught is equal to 8.85 times 10 to the power negative 12 farad per meter. Alright? Okay. So now, instead of just having air in there, we are going to fill it with some material called dielectric. So the property of dielectric material in general is like this. Let's suppose you have positive and negative plates. Then the material is in here. You fill this with this dielectric material. Then the property of this is that because this is positive charge and negative charge, there's electric field in that going in that direction. That's electric field. So that means positive charges will be pushed to the right and negative charges will be pushed to the left. So each molecule in that dielectric will polarize like negative, positive like that. And the next one will be negative, positive like that. Negative, positive like this. So the next one will be negative, positive, negative, positive. I'm not going to draw more. So negative, positive, negative, positive, negative, positive like that. And negative, positive, negative, positive. So you see on the surface, on this side is negative and on this side is positive because each molecule is polarized positive and negative charges like that because of the electric field. So if the electric field were directed in this direction, opposite way, this is a plus, this is a minus, negative plate, then it will be reversed. All the positive charges will be on the left and the negative charges will be on the right. So in this case, then the capacitance is, you can write it in this manner, is kappa epsilon naught A by D. Where A, of course, is in both cases, A is the area of these plates. So this area, that's area. D is the distance, the separation distance between the plates. Epsilon naught is this constant, permittivity of free space. And kappa is what we call the dielectric constant. So for each material, then they're different. Okay, so if you go and look at table 19.1, that's table 19.1, then you will see that, for example, like dry air, kappa for dry air is very close to 1, approximately equal to 1. That's why it's good to use just epsilon for air-filled capacitors. But for other material, like for example nylon, for nylon, it's the value they give is about 3.4. For example, for Teflon, I think it's TE, Teflon is 2.1, and so on. So they have a whole bunch of materials and these numbers given. So all you have to know is just you have to use this formula and go and look in the table. All right? So the only time you can use this formula is if it is vacuum or filled with dry air. Then you can use this formula without the kappa in it. And by the way, this is called Greek letter kappa. So it's like a K, it's like that. Okay? Now, so I'm going to do an example for you. And this example is related to exercise 19.8. Not exactly, it's related to example 19.8. What I'm going to do is, in that example, the two plates of area A is equal to 1 meter squared, and the distance is 1 millimeter wide and filled with air. So now I'm going to fill with Teflon, whose kappa is 2.1. In that case, what is the capacitance of this capacitor if I fill this with Teflon? So that's my question, right? I'm going to fill this with Teflon. So then I'll have to use this formula, which is C is equal to kappa epsilon naught A by D, right? So I just straightforward substitution. Kappa is 2.1 for Teflon. Epsilon naught is, as usual, 8.85 times 10 to the 1 negative 12 farad per meter. And A is 1 meter squared. And D is 1 times 10 to the 1 negative 3 meter, because that's 1 millimeter is 10 to the negative 3 meters. So now this is 10 to the negative 12, negative 3, so I'll get 10 to the negative 12 in the numerator, and I multiply 2.1 and 8.85 in the calculator, and I've done that already, and it's 18.59 times 10 to the 1 negative 9 farad, or 18.59 nanofarad. Okay, so 18.89 nanofarad. Every now and then I forgot to push the paper up, so you might miss 1 or 2 lines, so I'll make sure you see it. It's 18.59 nanofarad. Alright, so I'll see you in next video.